Thank you very much for having me. So I'm going to talk here today about proof-theoretic validity. One thing I want to emphasize is I am very keen for clarificatory questions. If I lose you at some point, I've likely lost far more than you. So be the brave person and say, Will, can you say that again? I'm more than happy to go over and try and say things slower if people are getting lost. Okay, so to start with the narrative that this project fits into, I need to start with Genson. So Genson, in developing the natural deduction calculus, highlights how the introduction and the elimination rules are related. And he does this in a very commonly quoted passage that I'm going to read to you now. So the introductions represent, as it were, the definitions of the symbols concerned, and the eliminations are no more, in the final analysis, than the consequences of these definitions. This fact may be expressed as follows. In eliminating a symbol, we may use the formula whose terminal symbol we are dealing only in the sense afforded by its introduction. We can illustrate this by looking at implication. The meaning of implication given by the introduction rule is something like, there's a method of going from A to B. The elimination rule can then be understood as telling us, given A, and A implies B, which has as its meaning a method from A to B, we can conclude B. Prowitz gives us a way of looking at this more formally. Recall that a detour in a proof is where one introduces, then eliminates a symbol. So up here now we have a detour for implication. And a logic normalizes if we can remove all detours. Prowitz improving normalization for intuitionistic logic showed us how to formally capture Genson's idea. And that's the idea that the meaning given by the introduction rules can be captured by just having the introduction right there, as we do, and then we apply the elimination rule. Then the reduction on detours as used in the proof of normalization shows us how the elimination rule follows from the introduction rule. It shows us how these rules are removable. We could have used the meaning of implication directly, as shown by the second proof, without writing the implication down and without applying the elimination rule. Prowitz then uses this to develop a notion of validity on arguments, where an argument is something that looks like a proof. Formally, we could think of it as a tree with nodes labeled by formulas and a discharge relation. So, for example, this proof that we know and love is an argument, but this kind of absurd graph with discharge relations is also an argument. And this gives us an extremely rough first blush of proof-theoretic validity, where we can say that an argument is valid if every one of its steps is either an introduction rule for the intuitionistic logic, or is one, or we have dealt with assumptions, turns out to be unnecessary for proving the conclusion. Proof-theoretic validity then is supposed to tell us which arguments follow from the meanings we have given the connectives by the introduction rules. And if it achieves this goal, then it shows us that the intuitionistic elimination rules follow from the meaning of the connectives when given by the standard introduction rules. If this is correct, it's a bold and exciting claim, for it's essentially the claim that we have shown that intuitionistic logic is analytic. A bolder conjecture has been made in intuitionistic logic's favor, however. suggesting that it's actually the strongest logic that has this property. To describe this, it helps to import the notion of completeness into this setting. To say a logic is complete with regards to proof-theoretic validity is to say that the arguments proof-theoretic validity labels valid are just the same as those the logic can construct as proofs. Prowich conjectured that intuitionistic logic was sound and complete for proof-theoretic validity. If this is true, it would suggest that intuitionistic logic is uniquely privileged in being the logic that we get from the meanings of these introduction rules alone. And this certainly makes the idea worthy of further attention. Well, except that in 2019, Picker and Schroeder-Heister rather comprehensively refuted it. There have been previous results in this direction, but they managed to give a sufficiently general proof to rule out most modifications. And if you're at all interested in this, I really suggest their paper. It's quite interesting, and it's sufficiently general that the proof will work for systems other than proof-theoretic validity. Now, proof-theoretically valid arguments aren't closed under substitution, and so one of the early suggestions to deal with seeming failures of Prowitz's conjecture was to instead restrict only to those arguments that are closed under substitution. But Picker and Schroeder-Heister's result actually shows that this isn't going to work either. Well, except there is one notion of proof-theoretic validity that is sound and complete for intuitionistic logic when closed under substitution. And this is Goldbergs' modification of Dummett's proposal. I'm going to talk more about that later on. So given that Prowitz's conjecture fails, we might wonder why. One option is that intuitionistic logic just doesn't have the special property that Prowitz's conjecture suggests for it. It's just not the strongest logic that follows from the standard introduction rules, rather some super intuitionistic logic is. But another possibility is that proof-theoretic valid arguments don't follow from the meaning of the connectives alone. We've done something wrong in the definition of proof-theoretic validity, and this has led to the super-intuitionistic results. So the claim I'm going to make here is that arguments can be proof-theoretically valid due to the meanings assigned to the atomic formulas. So that's siding with point 2 here. There's something going on in the definition of proof-theoretic validity that means that some proof-theoretically valid arguments follow from something other than the meaning of the connectives, namely the meaning we've assigned to the atomic formulas. And then my second claim is going to be that the treatment of the atomic formulas can be generalized. And when we do that, intuitionistic logic will be sound and complete for proof-theoretic validity. So if I was to make a bold claim, I would say something like, so intuitionistic logic is the unique logic that follows from the meaning of the connectives given the introduction rules. I'm not going to make that bold claim. I'm just going to have it a question mark there. It becomes open again once we introduce this new way of considering proof-theoretic validity. Okay, so that was kind of a story to situate what I'm going to talk about here. But what I'm actually going to talk about, well, first I'm going to introduce proof-theoretic validity. And I'm going to get frustrated that I can't draw diagrams for you. Then I'm going to talk about why we might be worried that this turns out not to be intuitionistic logic, independent of our opinion of the status of intuitionistic logic. And I'm going to do this by claiming that the particular super intuitionistic validities that we end up having be proof theoretically valid are worrisome in that they don't appear to be harmonious. So it looks like proof theoretic validity and harmony are coming apart, and that's kind of surprising. maybe even worrying. Then I'm going to look at why it is that we get these super intuitionistic validities, and I'm going to try and illustrate how the atomic formulas are having a kind of large role in what's going on here. And then finally, I'm going to suggest a generalized treatment of the atomic formulas and sketch a proof, very sketchy, draw the outline of how we would show that the resulting system does capture intuitionistic logic. Okay, so let's start with proof-theoretic validity. So to begin with, we're going to need to decide what we're doing with our base case. Proof-theoretic validity is going to tell you when proofs are valid or arguments are valid, these more general structures, but sometimes you'll just have an atomic formula and you'll need to know what to do then. And so to deal with this, we're going to introduce atomic rules. Atomic rules come in two varieties. They might just be axioms that tell you can state a certain atomic formula, or they might be inferences from a certain number of atomic premises to an atomic conclusion. Two things to note here. The first is falsum is going to be treated like it's an atomic formula. The second is we're going to kind of wave our hands around the fact that we always have falsum implies P for every atomic formula P to ensure that it has the correct definition in the setting. Okay, so just for ease, let's call the collection of all atomic rules Blackboard S. And then any set of atomic rules is going to be called an atomic rule set. And any collection of atomic rule sets is going to be a proof-theoretic system. And when we define proof-theoretic validity, we're going to need an atomic rule set and a proof-theoretic system. And you'll see why shortly. Yeah, so it's going to be relative to the two of them. So the definition is going to be built up of 4 cases to deal with any way that a argument, where that's that tree structure with a discharge relation that may or may not be a proof, any way an argument can be presented to us. So for our base case, we're going to deal with closed arguments that end in atomic formulas, and then we're going to have 3 inductive cases. The first will deal with closed arguments that end in introduction rules. Then there will be closed arguments that don't end in introduction rules or atomic formulas. You can think of these as being the ones that end in elimination rules. And then finally, we're going to have a case that deals with open assumptions, so proofs that aren't closed. So what do we do in our base case? So given a proof of some atomic formula P, we're going to say it's S valid, just in case there's a proof of P using only rules in S. Remember, S is just a set of rules that only involve atomic formulas, so it's going to be the right kind of thing to do this. So imagine we have some set S that has the axioms P and R, then an inference from P to Q, and another inference from Q and R to S. Well, in this case, we're going to be able to construct a S-valid proof of little s, simply by sticking these rules together, as I've done here. Okay, so what about the inductive cases? So let's say you have an argument that ends in an introduction rule. Well, we're taking introduction rules to define the connectives. And so this essentially guarantees the application of an introduction rule is fine and dandy whenever we do it. And so all we need to do to make sure we can apply an introduction rule is check that our premises are satisfactorily proven. So given an argument, a closed argument that ends in an introduction rule, it's going to be S-valid if the arguments for its premises are S-valid. So for example here, if our S consists of just the axioms P and Q, and we have a proof of P and Q, we're going to see that this argument is S-valid because when we check the two premises, they're both S valid by our conditions for proofs that end in atomic formulas. Okay, so what about an argument that doesn't end in an introduction rule and it doesn't end in an atomic formula? Well, it's just going to be S valid if we can find another proof that does end in an introduction rule or possibly an atomic formula that is S valid. So we're just going to trade it for another proof that has the same conclusion, that has the property we want. So for example, we might have this proof here where we're doing that detour we saw before. We're introducing arrow and then we're eliminating it. It's closed. So we want to check if this is S valid. And the way we're going to do it is we're going to go and look for another proof of our conclusion Q that meets one of our previous two conditions. So in this case, we see that given our set S, we have such a proof where we use the axiom P and then we infer to Q. And so that tells us that our other proof is also S valid. So we only have one.
Can I ask a question, Will?
Yeah.
On that previous slide.
Yeah.
But the Q here is an atomic formula, right?
Yeah. Yeah.
Okay.
So yeah, so there are two ways we could deal with this. So one thing is
I was misparsing where the or went. Got it. It's not that the negation is not outside the or in the title of the slide here.
Right. Yes.
Got it.
Yes.
Got it.
Right.
Got it. Yes. That either don't end introduction rules or don't end in atomic formulas. Okay.
Yeah.
Got it. I'm happy. I'm sorry.
Right. No worries. All right. Great. Thank you for interrupting.
Thanks for answering.
So the last condition we have is when we're dealing with open assumptions. So if we have an argument with open assumptions, we're going to say it's S valid if there are proofs, closed proofs of those assumptions, and we substitute them in, then the resulting proof is closed. Okay, but wait, what if we can't find any proofs of our assumptions, particularly closed S valid proofs? So we might have this problem, and this is where the fact that we have a proof-theoretic system is going to come into play. So instead of just checking for closed S valid proofs, we're in fact going to search for valid proofs in any atomic rule system S prime in our proof-theoretic system that extends S. So it might be that we need to add in some extra atomic rules, and so we're going to be able to do that. And this will give us the condition that if an argument has open assumptions, then it's going to be S valid if the proof that results from replacing the assumptions with closed S prime valid proofs, where S prime is in our proof-theoretic system and extends our initial atomic rule set, then the resulting proof is S prime valid. So to give an example, let's say that we have this open proof where we are dealing with just modus ponens, but for atomic formulas here. And let S be the empty set. So that means we definitely can't prove either of our assumptions in S. What this condition tells us to do is to go and find some S prime where we can prove our assumptions. In fact, go and find every S prime where we can. So let's hop over to the one we were dealing with earlier, where we have the axiom P and the inference from P to Q. Now that we have these two rules, we're able to prove our two assumptions using closed proofs. And we're back with a proof that we know how to deal with using the closed assumptions we have running around. So that's basically proof-theoretic validity, or it's at least one version of it. People have played with basically every single one of the conditions. Some people split the arguments up in different ways, but this will do as a kind of sufficiently general idea of what proof-theoretic validity is for our purposes. And we can kind of think of there being lots of different proof-theoretic systems, depending on how we decide to define our collection of atomic rule set. And each of them will give us a different notion of what proof-theoretic validity is. And then what Schroeder, Heister, and Pica's result does is show that pretty much any way we pick it, we're not getting intuitionistic logic. Now, we don't have to deal directly with the proofs. We can define a consequence relation using the notion of proof-theoretic validity. This is where I'm really frustrated that I can't draw, because I'd really like to show you that each of these conditions hold, but I didn't have the foresight to make the proofs. So we basically get, first of all, the condition that we can prove P, just in case we can construct a proof of P using our system S. That's what this means. It means you can construct a proof of P using S. Then, because we allow Falsum to hang out in our systems, we just treat Falsum like it was an atomic formula. This is probably one of the oddest features of proof-theoretic validity when you line it up with more familiar consequence relations. Then say we're dealing with something like phi and psi, it's going to turn out that our condition for closed proofs, where we go and find some proof where we apply the introduction rules, means that we can treat this as being equivalent to us having a proof of phi and as having a proof of psi, right? Whenever we have a valid proof of phi and psi, it's going to mean we have a valid proof of phi and we have a valid proof of psi, because we know that we have a proof that ends in an introduction rule. Similarly, if we have a closed valid proof of phi or psi, it means we're either going to have a closed valid proof of phi or we're going to have a closed valid proof of psi, because it's going to have a proof that ends in an introduction rule. The only one of these that's slightly tricky is what happens when we have an implication. So let's say I have a closed valid proof of phi implies psi. Well, what does that mean? Well, it means I have a closed valid proof that ends in an introduction. And that means I have an open proof that has phi as a solution and psi as a conclusion. So I'm going to need to use the condition for open proofs here. And so for phi implies psi to follow, it means that every extension of my atomic rule set S that proves phi is also going to have to prove psi. So this isn't a new notion. This is just a nicer way of writing down the conditions I just gave you. Easier to work with. Okay, so that's my quick rundown of what proof-theoretic validity is. And so now I've done that, I'm going to change gears slightly, and I'm going to try and explain to you why I'm worried about proof-theoretic validity being super intuitionistic.
Will, before you change gears, can I get a quick clarification on the previous slide?
Absolutely.
Could you back up and explain what is going on with Falsum there? I think I just missed it.
Yeah, so basically proof-theoretic validity treats Falsum as something you can prove. When you can prove it, you can prove everything else. But it's completely allowable to have a atomic rule set that proves Falsum. And so the condition for Falsum is just going to be when you can prove it, when you have a proof from S, then it's good. We can change this for a less counterintuitive condition if we make a certain modification to what we consider an acceptable proof-theoretic system, and that's just we insist that it isn't allowed to prove Falsum. Then you can swap this for just it doesn't prove Falsum, which is what you would expect. Okay. And thanks again for interrupting. Interruptions are great. So changing gears slightly to talk about harmony and the super intuitionistic rules that turn out to be proof theoretically valid. So first of all, just quickly, what's harmony? So earlier in the beginning, when I was talking about the kind of motivation for proof theoretic validity, I talked about Genson's idea, and then I talked about Proutz's proof of normalization. And one thing that both of these show is that there's a particular nice symmetry between the introduction and the elimination rules for the intuitionistic connectives. And we might call this something like harmony. They're in harmony with one another. Now, it turns out that not all connectives have this property. So I have thrown up here the rules for tonk, and tonk's a pretty nasty connective. It has the introduction rule for or and the elimination rule for and. And because of this, in any system with just one theorem, it's going to prove a contradiction. So because of this, there's been a move to try and restrict which sets of atomic rules, sorry, not atomic rules, which sets of proof rules one can say define a connective. And so these conditions are sometimes called harmonies. They're supposed to be a harmony condition, which is where the introduction and elimination rule is supposed to have that kind of property we were appealing to in the beginning. Now, the rule that turns out to show up all the place when you're talking about proof theoretic validity is Harrop's rule. And this is the rule that Picker and Schroeder-Heister use in their proof. What Harrop's rule does is it says that if you have a negated antecedent and a disjunctive consequence, then you can push the implication through the disjunction. You might be more familiar with it as an axiom where it's called the Kreisel-Putnam axiom. And so what I'm going to argue right now is that Harrop's rule isn't harmonious. Now, to make sense of that, I'm going to have to treat it as either an introduction or an elimination rule. I'm going to treat it as an elimination rule. And here's why. In proof theoretic validity, we've specified our introduction rules. We know exactly what they are. They're the ones that we can just use whenever we like because they give the meanings to the connectives. Because Harrop's rule ends up being proof theoretically valid, but isn't one of our specified introduction rules, it's therefore going to need to be categorized as an elimination rule. So I'm going to treat this as an elimination rule for implication. Okay, and so there are several kind of technical definitions of harmony. One is conservativity. When you add it to a system, you shouldn't be able to prove more than you can already in the system. Whether or not Harrop's rule is conservative, I don't know. I think that's an open technical question. Then another notion is local detour elimination. That's what we saw at the beginning when we were doing the reductions. And then there are notions like general elimination harmony. In the questions, I'm happy to talk more about conservativity and general elimination harmony. But because local detour elimination played such a prominent role in the justification for proof theoretic validity, I'm going to focus on the fact that I don't think that Harrop's rule is harmonious in the sense of local detour elimination. Okay, so what's a local detour? Well, it's when you introduce and eliminate a connective, and being able to eliminate these or reduce these means that you can kind of take your premises and give a proof of your conclusion. Here's the one for and. We saw the one for implication earlier. Clearly, tonk doesn't have this property. So then we have this question, well, does Harrop's rule, as treated as an elimination rule for implication, have this property? If we have a proof where we introduce implication and then we eliminate it, can we get rid of that use of Harrop's rule? And I am claiming that the answer is no. And the answer is no. The reason the answer is no is because Harrop's rule is admissible, but not derivable in intuitionistic logic. And what that's going to mean is that there are going to be certain proofs in intuitionistic logic that have assumptions where the application of Harrop's rule is going to go beyond the information imparted by the intuitionistic introduction rules. So here's a proof where we have a completely fine intuitionistic proof up until not A implies B or C, and then we apply Harrop's rule. Now, if we could get rid of this, we would need to be able to find a proof of this conclusion that ends in the introduction of or. Now, it might be inside an or elimination, but it would still need to end with or introduction. And it turns out we can't do this. And one reason to see this is just that this result here isn't intuitionistically provable. And so we're not going to be able to find that proof. So my claim is that this makes Harrop's rule in this context inharmonious with the intuitionistic introduction rules. And this is really, I think, surprising because proof-theoretic validity was supposed to just tell us what follows from the meanings of the intuitionistic introduction rules. And so everything that comes out as proof-theoretically valid should be in harmony with them. Now, we can get an idea of why this might be happening by considering a double detour. So this is where you first introduce or, and then you introduce arrow, then apply Harrop's rule. Now, whenever this is the case, we can remove the use of Harrop's rule. The only problem is, as we just saw, sometimes you can't have a double detour because you have assumptions. So we might think one of our questions would be, why is it in proof-theoretic validity that you end up being able to eliminate these Harrop's rule, you end up having these double detours? Can I ask Sean quickly, when did we start?
About 7 after.
Okay, all right. So I have more than 20 minutes left.
Yes.
Great, all right. My timing is not completely off. Okay, so we've seen there's going to be some kind of connection with double detours, and that seems like it might have something to do with the meaning of the intuitionistic connectives as given by the introduction rules. Might it be that what's happening is that proof-theoretic validity is accidentally overzealous in its elimination of detours? And that's why we're getting things like Harrop's rule. Well, Picker and Schroeder-Heister in their proof attribute this Harrop's rule showing up to a property called export. What export means is that whenever we have a set of atomic rules, we can swap it instead for assumptions. And when we have assumptions, we can swap it for atomic rules. And that instead suggests that something is going on with the atomic formulas, but as stated in that way, it's just not clear what's happening with the proofs. So what I think is happening is that the treatment of the atomic formulas is leading to double detours being available. And when double detours aren't available, it's because some other super intuitionistic formula is going to be valid. And so that's what's going on. The treatment of the atomic formulas is insufficiently general in that one way of treating them is going to make one super intuitionistic validity valid. And then when we try and remove that, we get another one instead. Okay, so I'm going to do 2 examples of proof-theoretic systems and look at what ends up being proof-theoretically valid on them. I don't know why I called them frames here, probably because I'm going to talk about crippy frames in the next section. But these are proof-theoretic systems. They're sets of rules. And I'm just going to take two real toy systems. Like, these are very small, very odd. So the first one here consists of 3 atomic rule sets. One's just the empty set. And then we have another one that lets us prove P, and then via that Q. And then the other one lets us prove P and via that R. And you can think of one way of many in which this is not a very general proof-theoretic system in its treatment of the atomic formulas, is that P here is either coupled with Q or it's coupled with R. And one way we might try and fix that is by just adding the axiom, the axiom P all on its own. That seems like one of the things that's missing from the initial proof-theoretic system. And then because these arrows are subsets, we don't get to pick what the relations is, and we end up with a proof-theoretic system that looks like this. Okay, so I'm just going to talk about what's valid on these, and it might seem irrelevant to start with, but it's going to lead back to Harrop's rule. Okay, so let's take that second system, the one where we have this set of P all on its own. So in this system, the one-step inference that goes from P to Q or R is going to be invalid relative to the empty set. Just a note, the reason that I am working on using empty set invalidity is because whatever's valid on the empty set is going to be valid on every other atomic rule set in the proof-theoretic system. And so we might say valid on the proof-theoretic system itself. Okay, but the inference, the one-step inference from P to Q or R is going to empty set valid. Okay, so why is that? Well, this is an open proof or an open argument. So the first thing we're going to need to do is use our condition for open arguments. And we're going to need to go off and find a proof of P and then check validity relative to the atomic system where we can find a proof of P. There's no proof of P in the empty set, but we do have a proof of P in the set that consists of just the axiom P. However, we can't find any proof of Q or R here. And so it's going to turn out that the one-step inference won't be valid. Okay, so what about our other proof-theoretic system? So now we've lost that set that contains just the proof of P. And it turns out that's going to mean that this one-step inference is valid. So again, we do exactly the same thing. We can't find a proof of P in the empty set, so we're going to go off to the places where we can find one. And now we find it in 2 places. We find one in our system that lets us also prove Q, or our atomic rule set that lets us also prove Q, and the other in the rule set that also lets us prove R. Now we need to check if our one-step inference to Q or R is valid in each of these separately. So first we go over to P and P implies Q. And there we see that we do have a completely good proof of Q or R using OR introduction on Q, which we can get from P. Then we go over to the other side and we do exactly the same thing, except now we find a proof of R and therefore P, so therefore Q or R. And so in this way, we see that this one-step inference is empty set valid on this proof-theoretic system. So that's going to mean that obviously this is a super classical, in this case, inference that's valid on this setting. So this isn't a good and general proof-theoretic system. But using this distinction between whether this one-step inference is valid or not, we can see how a Harrop's-like rule ends up being valid on what seemed like the more general system. And while these are just toy examples, this is replicating what's happening on larger, more reputable proof-theoretic systems that might seem like they have a completely general treatment of the atomic formulas. So one thing to note is this isn't a schema, because proof-theoretic systems are generally not closed under substitution. Proof-theoretic validity is generally not closed under substitution. So we really do mean the atomic formulas here, or I really mean the atomic formulas here. Okay, so it turns out on the two systems we were thinking about, this Harrop's-like rule is going to be valid on the empty set only when that one-step inference isn't going to be. And the general idea here is whether we can construct a double detour or not. And so when we do have the step from P to QRR being valid, we're not going to be able to construct a double detour. And so the Harrop's-like rule isn't going to be proof theoretically valid. But let's say that again more slowly. So if P, therefore Q or R, is empty set valid, then it follows by the condition for open arguments, where we have to substitute any proof we can find of this in, that the following has to be empty set valid, because this is a closed proof of P, therefore Q or R. Now, given the condition for closed non-introductory arguments, that means we're going to have to find an empty set valid argument that ends in an introduction rule. And because it ends in an introduction rule and the last rule is an R, that means either we're going to have a derivation of P implies Q or a derivation of P implies R. And whichever one we have, it's going to have to be valid, again, relative to the empty set. But in both of our proof-theoretic systems, it's not the case that P implies Q or P implies R is empty set valid, because we can always find some system that proves P and doesn't prove Q, and we can find a system that proves P and can't prove R. So we're not going to have either of these proofs being valid, and that means that this whole thing is going to be invalid, and so this guy can't be valid. We found a counterexample using substitution of the proof, that substitution of the open assumption. Okay, so what do I want to take away from what I just showed you? What I want to take away is that when we think that we have a less than general treatment of the atomic formulas, it's making these one-step inferences valid, and we try and get rid of it for what we think is a more general treatment, we actually don't succeed in doing that, because we end up forcing certain proofs to be possible, in particular the double detour proofs. But if we had been able to consider both treatments of the atomic formulas at once, we wouldn't have had this problem. The reason that we can't define a proof-theoretic system that considers both treatments at once is because we're stuck with subsets. We can only have one set that has a particular P in it, for example, and so we can't have it mimicking the behavior of both systems. And that leads to the solution I'm going to propose. So this is going to mean that we return to Goldbergs. And what Goldberg managed to do is get closer to intuitionistic logic than almost any other option on the market, as it were. Still needs schematic closure, but that's still good compared to the systems that contain Kreisel-Putnam logic. So how did he get so close to intuitionistic logic? Well, he doesn't put it this way, but we can see it as follows. He does it by taking a set G of proof-theoretic systems and then defining proof-theoretic validity relative to that set of proof-theoretic systems. So rather than asking what's valid on a proof-theoretic system and then looking at each of the atomic rule sets, he looks at what's valid on every single one of the proof-theoretic systems. And this is going to kick out super intuitionistic inferences, but not all of them, because you still need to take substitution closure. So here's my proposal. Let's just generalize what Goldberg was doing. Rather than considering a restricted set of the proof-theoretic systems, let's just ask what's proof-theoretically valid on every proof-theoretic system and say that that's how we get to proof-theoretic validity. That's what we need to do to have a completely general treatment of the atomic formulas. And the goal of this last section, which I'm going to try and do in about 10 minutes, maybe less, is to show that if we do this, we get something that's sound and complete for intuitionistic logic, or that intuitionistic logic is sound and complete for. So one way of thinking about what's being proposed here is that on the old way of thinking, atomic rule sets were treated as analogous to models, and then proof-theoretic systems were treated as analogous to classes of models. And what I want to do, co-propose a new way of thinking about it, where atomic rule sets are analogous to worlds, and proof-theoretic systems are now analogous to models. And so we define proof-theoretic validity over a collection of proof-theoretic systems. And I'm going to try and show that this solves our problem with super intuitionistic inferences. And I'm going to do this basically by just picking a sound and complete collection of crippy frames and showing that we can find an equivalent proof-theoretic system for each of them. So a crippy frame, an intuitionistic crippy frame, is going to be a pair consisting of a set of worlds and an accessibility relation, which is a preorder. A crippy frame, a crippy model is then just a crippy frame plus a monotonic valuation function. And we're going to call a crippy frame finite just in case the set of worlds is finite. Though it still may force infinitely many atomic formulas. Now, there's a pretty nice comparison between how consequence is defined on crippy models and how it and our kind of derived consequence relation for proof-theoretic validity. For the case of atomic formulas, we just replace being provable given the rules in the set S with being in the valuation at the world. For and or, the conditions are basically identical. Then for implication, rather than talking about extensions of our atomic rule set, we instead need to talk about worlds that are accessible from the initial world. The troublesome case is Folsom. I mentioned this earlier. We can actually change our definition of proof-theoretic systems so that we kick out everything that proves Folsom, and we won't actually change what the whole set of proof-theoretic systems, what's sound and complete for it. And so we can just change this condition to one that looks much more like intuitionistic logic, and then we'll have the same condition there as well. Okay, so like I said, the game that's being played here is to find a collection of crippy models. In this case, the finite crippy models that are sound and complete for intuitionistic logic, and then show that for every crippy model, there's a proof-theoretic system that agrees with it on the formulas. Okay, so there's a pretty straightforward way we could start trying to do this. So we could take a crippy model like this one here, and then we could note that the atomic formulas forced at each world can be dealt with by just adding in axioms. So we just say, well, if this world proves P, just add a atomic rule set that just has the axiom P. If this one does P and Q, just have one that just has the axioms P and Q. Now, there's an obvious difficulty with this. In a Kripke model, we might have two worlds that prove all the same atomic formulas, but are still distinct. Yet, if we do the naive translation into proof-theoretic systems, we're going to get that the subset relation on the proof-theoretic system doesn't match that of the Kripke model, and we're going to have less atomic rule sets than we have worlds. There's a really kind of clunky way to deal with this, but it works. We don't just have axioms running around. We also have inferences from atomic formulas to atomic formulas. And some of those inferences are essentially just going to be tautologies. They're not going to affect what's proven or not provable from a particular atomic rule set, namely the inferences that just go from something like T to T or P to P. So we can use those to essentially be world labels. Like here I've stuck in TT and here I've stuck in SS. And that means even though these are still going to prove the same things, they're now distinct sets of atomic rules. And so that's basically the technique that's going to be used. So for every finite Kripke model, pick a unique atomic formula for each world. So we're just going to label certain atomic formulas by worlds. And then this lets us give the following definition of a proof-theoretic system for each finite Kripke model. You define the proof-theoretic system such that it has an atomic rule set for each world that's going to contain an axiom for every atomic formula that's forced on that world. And then it's going to contain the world labels, essentially, for every world that is that accesses this world. So, and we're going to do that using trivial inferences from P to P. Okay, and now my claim is that if we do this, we're going to get exactly the same formulas true on each point in these in the Kripke model on one side and then the proof-theoretic system on the other. I'm just going to put this up for people to contemplate. I don't find it's helpful to talk through proofs, but if you don't believe me, this is kind of the quickest way to try and convince you. But I take it that once we've managed to do this, once we've managed to show that we can interpret the Kripke models into the proof-theoretic systems, that means that if we take the collection of all proof-theoretic systems, we do have a notion that's going to be sound and complete for intuitionistic logic. And this means we've managed to kind of save proof-theoretic validity from Peker and Schroeder-Heist as a result. And in fact, if you look at what we've done here, what we've done is we've blocked export from working. And so that's why we've managed to get intuitionistic logic here. All right, thank you very much. That's my talk, and I'm going to shut up now.